Hello, I've been requested to give a little mini lecture over 6.8. It's got the exponential growth and decay. So I'm gonna have a three-part lecture. This is part one, and this lecture refers to basically this exponential function right here. It's n of t equals n sub 0 e to the kt. Now every letter in this formula means something. The n sub 0 represents the initial amount of a substance. Now that substance could be people. It could be bacteria, it could be humans, it could be some kind of radioactive substance. It's some kind of a population. And n sub 0 represents how many of those do you have at the beginning of the experiment. Uh, E, of course, is the Euler's function. It's the 2.718. K is the rate. And now, if it's K is a certain value, it's a growth rate. And if K is negative, if K could be a decay rate as well. T is time. And time could be in years, like it was on the continuous compound interest formula 6.7. But it may not. It could be in days. It could be hours. It could even be seconds. N is the amount at the end of the period. It's how much you have at the end of the experiment. Now, if it's growing, N will be more than n sub 0. If it's decaying, that means it's reducing in size. It's going to be less than what you have originally. And I have the formulas for that over here. If it's a growth, this is kind of what the model looks like. N sub 0 is what you have at time 0. So right there, we hit the y-axis is the n sub 0. And it grows and it grows and grows and it grows exponentially. At some point, it will double in size. And T is called the doubling time. So the time it takes to double in size is called the doubling time. If you look down here real quick, the key words are doubling time, and the K is the growth rate. So if K is positive, it will be growing. And so that's kind of how, so it's the same formula for both growth and decay, and you recognize its growth by looking at the K. If K is positive, you know it's growing, it's getting bigger. And if K is negative, it's going down in size. So growth indicates that K would be greater than 0. And like I said a while ago, N would be greater than n sub 0. So what you have at some time later in time will be more than what you had to start with. So, which makes sense. Now, key examples of situations, problems that you would have in exponential growth would be a bacteria. Bacteria will grow in size. Money. Some people's money will grow exponentially. We learned that in the continuous compounded interest in 6.7. As a matter of fact, this formula is the same formula that you had in 6.7, just kind of disguised a little bit. If you look at the old formula back in 6.7, it's A equals P times E to the RT power. So technically, it is the same formula. The P, remember, was the present value, what you have initially. Well, that's what n sub 0 is representing, is what you have initially. And E is the Euler's function. K is the exponential growth or decay. R was the rate, and but when you go with money, it's positive. And T was time, and A was the amount that you had at the end of the period, and that's what N is representing. So it's the same formula. Why don't they use the same formula? Well, this formula deals primarily when you're dealing with money, and this formula is pretty much everything else that grows exponentially. But this one is kind of a special case, actually. So, but anyway, and then the decay actually is going down in size. And so you have something what you have originally, and it's going down. And the K will be negative, so that's how you will know it's a decay problem, that the K is a negative number. And so N will be less than what you have initially. If you grow down in size, and notice it doesn't go into the negative direction. I mean, you cannot have a negative amount of a substance or a negative number of people. And but eventually it will get closer and closer to 0. This is like what exponential growth and exponential decay functions will do eventually. So this will come out here and it will half itself. This is called half-life. And that is some key words, half-life and the decay rate. The decay rate is when the K is negative. Examples of this would be carbon dating. They can tell how old a fossil is by how much carbon 14's in the mass. So comparatively to what it is with when it died. And then there's radioactive decay. is like when some like plutonium or uranium, when it's released into the ground or whatever, it starts decaying very slowly, but it does decay, and so it doesn't grow after it's been released. It starts decaying. Populations, as well as populations over here, they can be doing both. You can have one city growing and one city decaying in population. So I'm not sure if everybody's lived in a city or know about a city that is not as big as it used to be. So it could be growing, it could be decaying exponentially. And then there's some cities who hit a boom will grow exponentially. So that could be either way. So I've seen, you can talk about populations of deer on an island. There's some examples I've seen in books with that. But anyway, this is part 1 of 3, and part 2 and part 3 is going to be basically 2 problems. Part 2 will be is going to be a exponential growth type problem, and part 3 will be an exponential decay type problem. And this is the end of part 1 though.